So today we'll take up the 14th session on relative velocity. This will be in continuation to the theory of relative velocity as discussed in the 13th video. In the 13th video, we derived how velocity of a point P as seen from two mutually rotating frames M and F are related to each other, and how acceleration of point P in these two frames are related to each other. Okay. So first we'll discuss one more conceptual point regarding this concept, and then we'll take up some numerical to demonstrate this formulas. Okay. So it is important. See, for example, I would just like to say that in IIT JEE Advanced paper 2016, when IIT Guwahati set it, this type of rotating problems on rotating frames were asked. Full 8 marks question, 4 marks, 2 questions, 4 marks each. So it is very important, you have to know it. And plus one more thing, if you are preparing for JEE Advanced, then definitely you must have a complete understanding of this relative velocity theory, not only for translating frame but also for rotating frames. And this is also very important in the theory of pseudo forces, as we'll discuss in further in the coming videos on Newton's laws of motion. There also this theory is extremely important, so they have to be kept in mind. All right. So I'll write down that formula which I derived in the previous class, in the previous video. All right. So this is the frame F. All right. F is some reference frame. F is some reference frame. M is also some reference frame. M rotates with respect to F. At certain instant, angular velocity of M with respect to F is omega. Alright. Capital A is some fixed location of M. Point A is either a real location or imaginary location of frame M. Alright. Real location, imaginary location, they all have been fully explained in the 7th video. So I am emphasizing it again. Okay. And the link to all the previous videos will be given in the description box of this video. Okay. All the links to previous 13 videos, they will be given in the description box of this video. You can, from going to those links, you can access those videos also. Fine. So A is a location of M. That meaning A is either a real or a material location of M. And P is some arbitrary location, moving point. A to P vector is RPA, and beta is the angular acceleration of M with respect to F at time t. Omega is the angular velocity of M with respect to F at time t. So we derived the relation for VPF and VPM, okay, in the 13th video. That relation I'll write down here, okay. So VPF meaning velocity of point P with respect to frame F at time t, that is same as velocity of point P with respect to frame M at time t plus VAF plus omega cross RPA. This formula we have derived in the 13th video, 13th session. And we also found a relation for acceleration also. So I will write down, but before that I would like to make one point I would like to explain. See, if this point P is a real or imaginary location of M, in that case, VPM becomes 0. So see, in deriving this formula, P can be any arbitrary point. P need not be fixed with respect to M. P may be moving with respect to M also and moving with respect to F also, general case. But if you make one more assumption, if you impose one more condition, that if point P is a real or a material location of M, P is either a material point of M or its imaginary location. So if point P is a real or imaginary location of M, in that case, this will imply that VPM becomes 0. This VPM becomes 0. So this term will go away. In that case, we get the following relation. VPF is equal to VAF plus omega cross RPA. So this relates the velocities of two locations of a rotating rigid body M with respect to frame F. Okay, fine. So this relates velocity. This relates the velocity of a relation. This gives the relationship between velocities of two locations P and A, which are fixed in the rigid body M or its frame. Okay. So this gives the relation between the velocities between two locations of a rotating rigid body M with respect to frame F. So if P and A both are fixed with respect to M, then VPF is equal to VAF plus omega cross RP. Fine. So this gives the relationship between the velocities of two locations of M, namely the points P and A. And this relates the velocities of P and A with respect to frame F. Fine. So if P and, I am repeatedly repeating again, if P and A are two locations of M, and then M rotates with respect to F, then VPF and VAF are related by this equation. Fine. So this we have already discussed in the previous videos, that if a body M rotates with respect to F, then in general two locations of M will not have identical velocities with respect to F. So this equation gives the relationship between VPF and VAF, where P and A are two real or imaginary locations of frame M. Okay, so it gives the relation between the velocities of two locations P and A of M, and M rotates with respect to F. So this equation has to be kept in mind. Fine. Achha, now I'll grab it. Okay, fine. Now suppose we again remove the restriction that P is fixed with respect to M. We again take the general case. Fine. Now we before this I assumed just now that P was also fixed with respect to M. P was a real or a material point of M. Okay, but real or imaginary location of M. Okay, but now we remove that restriction again. Again we assume the general case that P is moving with respect to M also. But A is a fixed location of M. A is fixed with respect to M. Fine. So now we again assume that let P also move. Let P also move with respect to M. Let P also move with respect to M. That is, again we take the general case which we derived just now. So we write down that formula again, which we derived in the 13th session. Okay. So I'll write down that formula again, which I wrote initially today, before deriving that general relation. Okay. So VPF is equal to VPM plus VAF plus omega cross RPA. So VPF is equal to VPM plus VAF plus omega cross RPA. Fine. So now I would like to tell one thing. See, point P is situated here. Okay. Now point P may either lie on the coincide with one of the material points of M, that is its real location, or it may coincide with one of the imaginary locations of M. It can be either ways. So suppose P overlaps with another location P dash of M. So P dash is the location of M which is in contact with point P at time t. Fine. So P dash meaning a location of M. Location of M meaning either its real location or imaginary location. Location of M. Location of M meaning its real location or imaginary location. Real location meaning its material point. Suppose this pen, this is the material M. Suppose this pen, rigid body M, pen M is the pen. So this point is the material point. Any point where its matter exists, that is the material point. Fine. So this is the P dash is the location of M. So it's either a real location or imaginary location of M, which I fully explained in previous videos. So location of M and P dash is in contact with P at time t. Is in contact with P at time t. P dash is the location of M and P dash is in contact with P at time t. So this means vector from A to P will be same as the vector from A to P dash, because P and P dash overlap each other at that instant. So this means we can replace RPA by RPA is same as RP dash A. Okay, RP can be replaced by RP dash A because P and P dash coincide at time t. They are overlapping and A is here. So RPA is same as RP dash A. So now this formula we write here and now we replace RPA by RP dash A. Fine. Then what do we get? We get the relation VPF is equal to VPM plus VAF plus omega cross RP dash A. Instead of RPA we write RP dash A. Now we interchange the order of the terms. Vector addition is commutative. So this means VPF will be equal to VPM plus this term. I'll write it here again, okay? VAF plus omega cross RP dash A. Now see, before this I derived the general relation between velocities of two locations of M, A and P, where A and P are two locations of M, VPF equal to VAF plus omega cross RPA. That result we apply to this formula. So this quantity is nothing but the velocity of P dash with respect to F. P dash is the real or imaginary location of M. That meaning P dash is fixed with respect to M. So this quantity can be replaced by Vp dash F. So this means we get the following relation. VPF is equal to VPM plus Vp dash F. See, this relation is very important. It is an extremely important relation which is very useful for finding the velocity of a point P which moves with respect to a rotating frame M. This will be used in the angular momentum conservation problems. As we go to much further stage, angular momentum conservation problem, this relation will be very important. So what does it say? It means, it says that see, if M rotates with respect to F, fine. If M rotates with respect to F and A is a real or imaginary location of M and P is a moving point, P in general might be moving with respect to M. At time t, point P coincides with one location P dash of M. P dash again may be a real or imaginary location of M. Then this equation says that velocity of P with respect to F is equal to velocity of P with respect to M plus velocity of coincident location P dash of M with respect to F at that instant. So when we add these two terms, we get VPF. Okay. So this term, entire term is VP dash F. I'll rub this here, this just cause confusion. I'll write it here. This result is nothing but Vp dash F. So this result Vp dash F is same as replacing these two by Vp dash F. So VPF is equal to velocity of a point P with respect to frame F is equal to velocity of point P with respect to rotating frame M, where M rotates with respect to F, plus velocity of coincident location of M with respect to F. Coincident location, which location? P dash. So this means that velocity of point P with respect to F at time t is equal to velocity of point P with respect to a frame M which rotates with respect to F at time t plus velocity of coincident location P dash of M which overlaps with P at time t. Okay. So if we add these two terms, we get VPF. The velocity of P dash F. So P dash and P overlap each other at time t. So velocity of P with respect to F is equal to velocity of P with respect to M plus velocity of P dash with respect to F, where P dash and P overlap each other at time t. But P is fixed with respect to, P is not fixed with respect to M in general case, but P dash is a real or material point of M, real or imaginary location of M. So P dash and P overlap each other. So VPF is equal to VPM plus Vp dash F. So velocity of P with respect to F is equal to velocity of P with respect to M plus velocity of coincident location P dash of M with respect to F. If we add these two terms, we get VPF. Fine. Alright. So I'll rub it now. So this relation will be very useful. That's why I'm repeating it again. Fine. We can derive a similar relation for acceleration also. But in my opinion, that is not that much important as this relation. This is much more useful. So this is sufficient. Okay. So now I will take a problem to illustrate these formulas which we derived in the 13th session. Okay. So I will write down the problem here. It's a numerical problem. Okay. It's a numerical problem. I will take it up just now. See, the problem is this. Instead of F, we have the ground frame. Instead of F, we have the ground frame. Fine. So we denote ground frame by G. Fine. Then what we are given, this is the vertical XY plane. This is the vertical XY plane. Vertical XY plane is fixed with respect to ground. Okay. Coordinate system is fixed to the ground. This is the origin of the coordinate system. See, there is a rod, rigid rod. There is a rigid rod. Okay. Whose left end is at A1 is fixed with coincides with origin, and length of the rod is 10 meter. 10 meter is the length of the rod. Length of the rod is equal to 10 meter. Fine. This rod, left end of rod is A1, which is fixed in ground at O origin. So rod is rotating with respect to ground. It has some angular velocity omega. It has some angular acceleration beta. So omega is the angular velocity of rod with respect to ground at time t, and beta is the angular acceleration of rod with respect to ground at time t. Both are with respect to ground and both have the anti-clockwise sense. It is given that omega is given to be 4 radian per second. Omega is given to be 4 radian per second at that instant. This arrow indicates that its sense is anti-clockwise. And angular acceleration beta is given to be 2 radian per second. This is also an anti-clockwise second square, sorry. That is also an anti-clockwise sense. One more point you have to keep in mind is there is a ring which slides along the rod. Okay. At the given instant, this is the sliding ring, slider. We call it the slider. Slider. Okay. Slider or a ring. We should denote by P, say. At the instant shown, the slider is at a distance of, say, 6 meter from A1. It is at a distance of 6 meter. Fine. It is at a distance of, not 6 meter, let's call it, say, 8 meter. 8 meter. Fine. Call it. It's at a distance of 8 meter. And it has a velocity of, some velocity with respect to rod. It has some acceleration with respect to rod. So acceleration of the slider will be denoted by P, AP, and rod will be denoted by M. M will mean rod. Rod is a rigid body, so we denote it by M. Rod will be denoted by M. So rod rotates with respect to F, ground frame G. Fine. So instead of F we have ground frame G, and instead of rod we have this. Instead of rod, we denote it by M, is rotating body. This is the slider which is sliding. Its distance from left hand A1 is 8 meter at the given instant. Also, velocity of the slider, that is P, with respect to M, that is rod, is given to be 5 meter per second in rightward direction at the given instant. 5 meter per second at the given instant in rightward direction. Fine. And its acceleration with respect to rod, that is M, is given to be 3 meter per second square. This is also in rightward direction. Fine. So all the details have been fully given. So I'll repeat it. Instead of F, we have the ground frame G. Instead of a rod, we have the rod will be denoted by M. So rod rotates with respect to ground. that is m rotates with respect to ground. Its angular velocity omega and angular acceleration beta with respect to ground are as given here. Both are in the anti-clockwise sense. The slider is denoted by P. As time passes by, slider slides along the rod away from left hand A1. At the given instant, the slider is at a distance of 8 meters from the left hand A1. A1 coincides with origin. And its velocity of P, slider will be denoted by P. VPM meaning velocity of slider with respect to rod, which is 5 meters per second rightward. And APM is the acceleration of slider with respect to rod, that is 3 meters per second square, that is also rightward. Fine. And A2 is the midpoint of the rod. So A2 to A1 distance will be 5 meters. This is 5 meters, this is 10 meters, and this is 8 meters. And A3 is some location here. A3 is some location which is imaginary location of rod. And coordinates of A3 are given to be 3, 4. Both are in SI units, meters. Fine. Alright. So this is the detail. Okay. Now our aim is to find two things. Two things we have to find. First we have to find what is the value of VPG in IJ notation. And second we have to find what is APG. So we have to find these two things. We have to find VPG and we have to find APG. VPG meaning velocity of slider with respect to ground at the given instant in IJ notation. And APG meaning acceleration of slider with respect to ground at the given instant in IJ notation. So these two things we have to calculate. Okay. These two things have to be calculated. Fine. Okay. So in this video, I'll just calculate this VPG just now. And APG will be found in the next video, 15th session. Okay. So 15th session will be in continuation of this 14th session. So that we'll find out in the next session, we'll calculate. Okay. So this is the situation I have told you just now. So one more thing we have to note down, that we have to know this, first of all we have to find VPG. So rod rotates with respect to ground, you can see. Rod is rotating with respect to ground. Fine. So I'll rub it, okay. I'll rub it. This I have written, so I'll rub it now. So we have to find VPG first. VPG has to be evaluated in IJ notation. IJ notation, okay, fine. So now rod rotates with respect to ground and P moves with respect to rod. So G meaning ground and M meaning rod. So we have to find VPG. So for that first we have to we have to apply the formula VPF equal to VPM plus VAF plus omega cross RPA. Now in that derivation, capital A was some arbitrary location of M. So we have to first define point A. So any location fixed in the rod can be taken to be point capital A. So suppose we take A1 to be the point capital A. A1 is the left end of the rod, material point of the rod in contact with origin. And A1 is always fixed. So in case of rotating frame, instead of A, we take the point A1. Now what we do, we write down the general formula. Okay. So we write it like this. See, VPG equal to VPM plus VAF. Instead of A, we take A1. VA1F. Instead of F, we take G. Plus omega cross RPA. Instead of RPA, we write RP1A. Where RP1A, sorry, RPA1, sorry, A1. So this is how we write it out. Fine. So we get VPG, VPF instead of VPF, VPG, VPM, VPM, plus VAF, the VA1G, plus omega cross RPA, the omega cross RPA1. Now we have to evaluate all these terms and add them, we get VPG. Fine. So first we write VPM now. So what is VPM? Velocity of the slider with respect to rod. And that is given to be how much? That is given to be 5 meters per second in rightward direction. So velocity of VPM meaning velocity of the rod, slider P with respect to rod M. That is given to be 5 meters per second in rightward direction. So VPM will be written as 5i hat meter per second. So one thing has been found out. Now we have to know VA1G. A1 is the material point of rod M, which is fixed at origin. So VA1G is 0. It is rest. It is at rest. So this term goes away. Now we have to write down omega cross RPA1. Now to know omega cross RPA1, we should write down omega in vector form, IJK notation. Now omega is given to be 4 radian per second anti-clockwise. Omega is given to be 4 radian per second anti-clockwise. Now anti-clockwise omega meaning its direction is outward as per the right hand thumb rule, because omega is anti-clockwise like this. So find the direction of omega. What do? We take the right hand, fold the first 4 fingers along the sense of omega, keeping the thumb of right hand straight. So thumb points outward, that is the direction of omega. In this case, outward direction is just along the z-axis. So we write down like this. Omega will be equal to 4 magnitude of omega, which is 4 radian per second, into unit vector along direction of omega, which is along positive z-axis. And so unit vector along omega will be vector k hat. K hat is just the unit vector along positive z-axis. And RPA1 is the vector from A1 to P. So how much will RPA1 be? Tell me. RPA1 will be equal to A1 to P. That is just 8 meter. So RPA1 will be 8i hat. Now we substitute in this formula, we get VPG. So I write it here, okay? Fine. So how much will VPG come out to be? See, it's like this. VPG is equal to VPM. VPM is 5i hat plus VA1G. VA1G is 0 plus omega cross RPA1. Omega is 4k cross RPA1, that is 8i. So that becomes equal to 5i hat, 4 into 8, 32, and k hat cross I hat is j hat, unit vector along y-axis. So this comes out to be 32 into j hat meter per second. Okay, so this gives VPG, 5i hat plus 32 j hat meter per second. So this gives us VPG, 5i hat plus 32 j hat meter per second. That is the velocity of slider with respect to ground at the given instant in IJ notation. Okay, so in this case we have taken point A1 to be A. Now there is no restriction that we should take A1 to be A. We can take some other location of M also to be A. We can take A2, which is another midpoint of the rod M. That's also real or imaginary location. It's a real location of rod frame M. That also we can take as point A. We can take this point to be point A, other end of the rod. Yeah, we can take this imaginary location A3 to be the point A. So we can take any location of M if we take point A and we calculate VPG, we get the same expression. Alright, so now I close it. In the 15th session, we'll just continue with this numerical. Fine. We'll take up more examples. We'll solve this problem in various different ways also. Okay, so I rub it just now. Okay, fine. So this is the end of 14th session. We'll just continue with the 15th session. We'll continue with this numerical problem in the 15th session. We'll continue. Fine. So let's close it.